All right, so today we're going to be covering recursion. We might be able to get done with it today. If not, then we'll go ahead and finish it off on Wednesday. And then we'll get into the last major topic for the course, searching and sorting. So recursion is just simply any context in which something is self-referential. So for example, the motivating demonstration that I hinted at a while ago now is what we want to do is we want to print off a countdown, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and then blast off without the use of any loops. So this is a traditional for loop, of course, and we could change this into a while loop. We could change this into a do while loop. We could hard code it so that it prints 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off. But I want to make sure that we're using a variable to do this so that we can use like a countdown from 100 instead, right? So if I don't have a loop control structure to do this, what am I left with? Well, the only thing I'm left with are functions, right? So let's go ahead and create a function here. Well, it doesn't return anything just yet, called countdown. Right? And what it's going to do is this is going to print a countdown from n to 1, then blast off. All right? So obviously we need to take as input n because we need to know where we're going to start. So I'm going to go ahead and put n right there. Right? So if this prints a countdown from n down to n to 1, right? Then suppose that it's 10, right? Well, what do we do next? We need to print a countdown from 9 to 1, right? Suppose that it's 9. Now we need to print a countdown from 8 to 1, or 9 to 1, 8 to 1, 7 to 1, etc. Right? But we have a function to do that for us, countdown. So if the countdown is not where let's just take care of the simple case first, right? If n is equal to 0, right, then we're done with the countdown, right? And so what should we print? Blast off. All right, there we go. All right. Otherwise, if it's not 0, then we're not yet down to our countdown, right? If it's 10, then I want to do a countdown from 9 instead. If it's 5, I want to do a countdown from 4. Well, again, we have a function to do that for us, countdown, n minus 1. Okay? By subtracting 1, I'm going down to the next countdown that I want to output, right? This is what recursion is. One function calls itself one or more times. Now, what if I didn't have this condition right here? We go countdown of 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Then what? 0, negative 1, negative 2, negative 3, negative 4, right? We would have an infinite loop, but we're not using a loop anymore, right? We are using the function to simulate a loop for us. And that's what recursion is all about, basically. That you are using the call stack in order to get what you want. So let's go ahead and call this countdown of n and see that it actually works. GCC, I called this, I called it Fibonacci prematurely here, but that's okay. That's what we'll look at next. Right? Blast off. Uh-oh. What happened? I never actually printed the number, printf, %d, and the line, n, there we go. GCC, and run this. Now it's 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off. Right? Now again, what if I did, say, 15 instead? It would still work. It would go 15, 9, 8, 7, 6, 5, 4, 3, all the way down. Well, what if I did, say, 1 million? There we go. GCC. And in addition to this taking a long time, don't worry, it's probably going to die soon. Right? Now, why is that? Let's go over here to Python Tutor and understand, again, what's going on. For this, I'm going to go ahead and grab all this code, put it over here, but I don't want to do a million. I want to keep it small, so let's just do a countdown from 4. Okay? Zoom out a little bit. There we go. So as we run through this program, observe what happens. I'm going to call a function. When I call a function, what happens with the stack? a new stack frame appears in the top, right? Or in this visualization on the bottom, with a value of 4. Now, it's not 0, so we'll print it out, and there's the result up there. But now it's not 0, so what we're going to do is we're going to call countdown of 4 minus 1, in other words 3. In other words, we have another stack frame. Another stack frame. Another stack frame. Right? For every time we call countdown, we're just creating one stack frame. This is basically how we are doing the loop, right? Instead of having an index variable I, where we keep track of this stuff and we update I, we are keeping track of the I values using the program stack, right? These stack frames. We're abusing it though, right? Because when we get down here to 0, right, then everything will start going back, right? We start unrolling this recursion, going back down to 1, 2, 3, 4, right? In other words, we've abused the call stack in order to simulate a loop, right? Well, what happens when we abuse it too much? 1 million stack frames, right? What's going to happen when I have a stack frame, stack frame, stack frame, stack frame, stack frame all the way up? Eventually I'm going to run out of space on the stack. Remember, it's only about 8 megabytes. So what happens when it gets too full? Stack overflow, right? And that's what happens here. It probably it happened at about, a 250,000 or so, somewhere around there. 250,000 metadata along with the integers, et cetera, that kind of makes sense, right? But my stack is not meant to do this. It's not meant for deep recursion, okay? All right, so, but just in case you think that this is a toy example, it's not. Again, there are plenty of languages where recursion is the way that you do things, right? The functional programming languages. There are programming languages without any loops at all, right? And it's just a different way of thinking about things. It's a functional way of thinking about things, a more mathematical way of thinking about things. However, every programming language that I know of does support recursion, right? So again, what is recursion? In general, recursion is anything that has a self-reference, right? Encoding a function is recursive if it makes one or more calls to itself. You see this all the time in mathematics, right? Like self-similar sequences, we call them fractals, and then they become art, right? Fractal art, all this kind of stuff, right? Mandelbrot set is usually the Sierpinski triangle or something like that. It is an object that is defined in terms of itself. So, for example, the Sierpinski triangle. There we go. That's defined by this is the better one, right? A triangle in which you remove the middle triangle out of it. Then you repeat that operation. For each one of those subtriangles, you remove the middle triangle out of it. For each one of those subtriangles, you remove the middle. You do that infinitely, right? And it turns out that these things have fractal dimension, fractional dimension, right? That this is not a two-dimensional object anymore, mathematically, right? It's somewhere between 1 and 2 dimensions, right? Okay? It's a different notion of dimension, though. So you're abusing the call stack, right? You are, it's defined in terms of itself. Another one that you probably have seen before is the classic Fibonacci sequence, right? How many people have not seen Fibonacci? All right, good. Everybody's seen it, right? Here it is mathematically. It's a function that is defined in terms of itself. F of n, well, if n is 1, right, then the value is 1. If n is 2, then the value is 1. Otherwise, if it's 3, 4, 5, 6, n is, then what you do is you look at the 2 previous values in the sequence. So if I were to write out this sequence, right, the first 2 are going to be 1 and 1. Right? Now the next one is going to be the sum of the 2 previous values. So 1 plus 1 is 2. What's the next value in the sequence? 1 plus 2, 3. Right? The next value in the sequence is the 2 previous values, 2 and 3. So 5, 8, what else? 13, 21, 34, 55, 89, ... There we go. It's an infinite sequence, okay? And it's recursive because each element is defined in terms of the two previous elements. Technically, this is a difference equation. It's a linear homogeneous recurrence relation of degree 2. They're a dime a dozen. There's nothing special about the Fibonacci sequence other than it is used constantly as an example of how to do basic recursion. And it's both a good example and a bad example. It's a good example in that it is showing you how to do recursion simply. It's a bad example in that nobody cares about what the value of the Fibonacci sequence is. You would never find this in any real code base at all, right? But it's also, then I turn it back around and say that it's a good example of why you do not want to use recursion in general, right? Let's understand why. Let's come over here and actually implement it, right? So what I'm going to do is I'm going to immediately jump to a long variable instead of an int variable, right? Longs are going to be twice as big, not twice as big, but the number of bits is twice as big. But the largest value that they can represent is 2 to the 63 minus 1, which is much, much larger than 2.147 billion. Okay? Why? Because this Fibonacci sequence is growing exponentially, and I want to play around with larger and larger values. Okay? So Fibonacci, right? Int n, right? Help me out. How am I going to implement this Fibonacci recursively using this mathematical definition? These are what are called base cases right here. This is where no more recursion occurs, right? Just like a loop, you have three aspects of a loop: the beginning, the continuation, right? And then the update, the increment. Well, our beginning here is, well, whatever n is, but we have to have an ending point. When do you no longer do any recursion? Well, when n is 1, you don't make a recursive call. You just say it's 1. When n is 2, you don't make a recursive call, you just say that it's 1. So if n is 1 or n is 2, I will return a value of 1 because that's the value of the Fibonacci sequence. Now, it may or may not be required, but I'm going to go ahead and put an L after that. That labels it not as an integer, which is the default. That labels it as a long variable, which is still an integer. It's just that there are 64 bits in it instead of 32. Okay. Else, what's the recursive part? Well, n is not 1 or 2, so we need to call Fibonacci of n minus 1. Then we need to call Fibonacci of n minus 2, and we need to add them together. So return Fibonacci of n minus 1 plus Fibonacci of n minus 2. Right? Good? All right. Now let's not go nuts here. Let's go ahead and just compute the 10th Fibonacci number. Right? And long result is equal to Fibonacci of n. There we go. And let's print it out. I think it's du as a placeholder for longs. Printf fib of %d is equal to %du. So I'll print out n and the result. Let's find out. It's not du, it's ld, sorry. ld. All right. So the 10th Fibonacci number was, what was it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 55. If this is correct, you should get it. Yay. Let's go up to 11. Do we get 89? Yep. I'm convinced that this works. Pretty fast, too. Right? Let's go ahead and consult Wolfram Alpha here on the largest Fibonacci number less than 2 to the 63rd minus 1. In other words, that's the largest value that we could actually compute using a long value. So there it is. Come on. I want to know which one it is, though. 90th. There we go. So let's cut that back and only go to like 88 because we may or may not be off by 1. So let's go to 88. Okay. GCC. All right, it's taking a little bit more time than usual. Give me an estimate. How long do you think we should sit here and wait for this? A couple minutes? Yay? Hours? Okay, hours. I'm going to continue bidding here. Days? Weeks? Right. Try trillions and billions and trillions of years. Right. So, remember that it's this large. Right. I'm going to end up making that many function calls. If I make that many function calls, 1 million function calls per second even, right? Then that's going to be seconds to years. Right? It might not actually be centuries. There, 91,000 years. Okay, fine. Well, that's a low estimate on because we got fast computers nowadays, right? You could do 1, 2, 3. You could do 1 billion function calls a second. Right? All right, it's still going to take you almost a century. Right? And if you kick this up to say, now it's not going to be representable by a long, right? But if you kick this up to 1,000, well, Wolfram Alpha could do it. What's Fibonacci of 1,000? It's going to be this huge giant number, right? 10 to the 208. But you're going to end up doing that many function calls. Even if I gave you 10 to the, 1 trillion function calls per second. Right? How many years is that? Well, that's 179 times the age of the current age of the known universe, right? So even if you started this computation back at the beginning of the universe, you still have 178 more of those time frames to go, right? Just to compute the 1,000th Fibonacci number. That Wolfram Alpha, by the way, again, can do in a matter of seconds. What's the difference? The difference is they don't use recursion to do this. Right? Or at least they don't use just recursion to do this. The idea here is that you are doing redundant work. So for example, let me come back over here and kill this because it's never going to run. Right? What I'm going to do is I'm going to create, this is something you should never do in general, but int num function calls, right, is equal to 0. I'm going to create a global variable here, and every time you call the Fibonacci sequence, right, I'm going to go ahead and increment this. And I'm going to go ahead and print this out. How many function calls does it take to, function calls, %d. How many function calls does it take to compute even, say, the Fibonacci of 10? Okay. GCC. A dot out. 10. There we go. Make it actually doable. 109 function calls. Now you'll note that there is some relationship there to the actual Fibonacci sequence, that the number of function calls is going to grow exponentially. Right? Well, what about when I call Fibonacci of 10? Let me go ahead and modify this. So how many function calls do I make where I have Fibonacci of 3? Right? If n is equal to 3, what I'll do, then I'll go ahead and increment the number of calls. All right? And let's go ahead and bump this up to not too much, 15 or so. There we go. In other words, to compute the Fibonacci of 3, I am doing that 233 times. Why would you do the same thing 233 times? Right? If you're doing 1,000, you're going to end up doing it billions and billions and billions of times. Why are you doing the same thing over and over and over again? Right? Are you expecting different results? Fibonacci of 3 is not going to change. Right? So one of the disadvantages of recursion is that you risk doing redundant work. Right? So is recursion good or is it bad? Right? So here are some disadvantages. Right? One is you end up abusing the call stack, right, to do your work. Right? The call stack is small and defenseless. Right? Don't abuse it. Right? Recursion, or deep recursion, even moderately deep recursion, risks stack overflow. Right? As we saw in the first example, when I try to count down, the countdown is not even doing any redundant work. It's just going 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. But you would not even be able to do a loop simulation of even 250,000 things. You would immediately overflow your stack, right? Probably even less than that in practice. You risk redundant work, right? For example, Fibonacci of 10, right, or what makes the same calls over and over again, right? Recomputing the same values over and over, right? And that's how you end up with 96,000 years or whatever it was to compute that, or 179 universe time frames, right? Don't do that, right? Once you've computed something, that's it. Compute it once and be done with it. It's called caching or memoization, which is what we'll look at here in a second. Those are the disadvantages, right? You risk exponential time and overhead to do the recursion. Right? These are all objective measures. Right? Let's go ahead and think about the advantages. For that, I'm going to ask you. Well, if you did have to, do something mathematical like this, right? Gee, there's a one-to-one translation there. So, I mean, if you are going to do something like this, arguably recursion does have its place that, you can go ahead and things that are recursive, go ahead and do it, right, that way, right? Many problem-solving techniques or approaches are recursive in nature, right? For example, divide and conquer techniques. Right? Divide and conquer techniques where I don't know how to solve this problem, but if I break it up into a smaller problem, well, maybe I can deal with that smaller problem. Like, for example, adding a whole bunch of numbers, right? If you were doing this on a ledger, right, how would you go about doing that? Would you go the first one, plus the second one, plus the third one, right? Let's do it up here really quick. 10, 4, 7, 3, 2, 9, 5, 2, 7. Right? Do you have a running total in your mind? Like, okay, 14 plus 7 is 21. What do you do to make this quicker on a piece of paper? 14. Right? You don't have to think about it too much because now you don't have a running total that you have to keep track of in your mind. 10, 11, 7, and then 7 and 14. Okay, now continue. 14 and 10, 24. This is 11. That's going to be 25. 25 and 24, 49. Right? What did I do there? Right? I did recursion. Right? Instead of, okay, well, I can't handle all 8 or 7 of these numbers all at once. I'm going to go ahead and break it down. Instead, I'm going to break it down into 2 parts. The first half and then the second half. I'm going to break that down further because I still don't know how to add up 4 numbers in my head. Break it down to just 2 numbers. 2 numbers and 2 numbers. Divide and conquer. You divide it down to what, well, now I can't divide it any further, right? Because otherwise I'm not doing any operations. But I can add 2 numbers in my head, that's easy, and write it down. I can add 2 numbers in my head and write it down. I can add 2 numbers and write it down. I can add 2 numbers and write it down. And I can come up with a divide and conquer approach here that is much easier, at least conceptually. If you were to do this on a computer, yeah, it's easy conceptually, it's easy to code it, but you end up abusing the call stack to do this. Right? Many divide and conquer techniques, for example, adding up numbers, etc. Right? Searching and sorting, which is our next topic. Right? So for those of you that have seen recursion before, and if you had an advocate for it, like, this is cool, why did they say it was cool? What are the advantages? Or if you've read an article like that, nobody's ever, is this the first time, who's seen recursion before? All right, okay, 1, 2, all right. So in what context did you see it? Like, was there an advocate for it? Like, this is cool, you can get a lot of stuff done, whatever.
Well, it was just very CSE class.
Okay.
Our teacher just brushed over it.
Okay.
A guy in the class loved it, but
Okay. Why then?
he just thought it was cool.
Okay.
No real reason.
All right. Well, the shine comes off pretty quick once you see the consequences, right? So, other things, what do I have here as the good, right? It's a good way of thinking inductively, right? So it's a very mathematical way of thinking, right? Many functional programming languages use recursion as their basic structure, right? And if you read some advocates for it, they'll come up with, well, it's not that one. Sorry, is that it's simple, or that it's clean, or that it's mathematical, or beautiful, that it's easily understood, right? They're looking at it through rose-colored glasses. All of these things are completely subjective, right? Is it simple? One person's simple is another person's complicated. Is it clean? Again, that's a subjective. Is it beautiful? That's definitely subjective, right? All code is ugly at the end of the day. Why? Because all code is not English, right? English is ugly, right? But it can be beautiful, right? So again, these are all subjective things, okay? But what's objective? Anything that takes 179 universe time frames, right? That's bad. Right? All right. So now that we know the good, the bad, and the ugly, let's think about how to design recursive functions, and then let's think about how not to design them, okay? Or how to redesign them. So the same basic principles wherein you design a loop are at play here. You need a beginning, you need a continuation, do I continue recursing or not? And you need an end. I no longer need to recurse because I'm done with my computation and I need to return. Or at the end of your loop, when do I end my loop? I need to get out of this loop. Right? Every recursive function needs at least one or more base cases. The termination condition where you no longer the recursion is no longer performed. That's just like a loop termination condition. This loop cannot go on infinitely. Right? If it went on infinitely, then you would eventually get a stack overflow like we did before, right? Or you would just never stop. Some base cases may perform basic error handling or corner cases. For example, the Fibonacci sequence is not defined for negative values. So I could put in here, if n is less than 1, then I'll go ahead and printf or return some negative value here, right? And that's not really a base case, that's just error handling, okay? Otherwise, you make one or more recursive calls to the same function. But you need to make sure that you're making progress towards your base cases, just like you need to make progress towards your termination conditions in a loop. Right? For example, the progress that we made here was subtracting 1 or subtracting 2. That's making progress towards 1 and 2 as your base cases. Okay? The initial call to your recursive function is your initialization statement. For int I equals 0, that's where you start your loop. For int n equals, 10, that's your countdown start, right? Because you're going down in it, right? That's basically how you design recursive functions, okay? Now, how do you eliminate them, right? And why do we want to eliminate them, right? Recursion can be bad, right? Inefficient, right? In fact, some programming guides either discourage or even prohibit recursion because of the risks of, for example, if you're in an embedded system, no way do you want to abuse the call stack. If you're in an embedded system, your call stack is measured maybe in kilobytes, right, instead of megabytes, in which case, nope, not at all, right? In fact, entire organizations have banned recursive code. For example, NASA. NASA does not allow any recursion or non-tail recursion, I forget what the details are, in their code bases. It's forbidden, right? Don't do this because it risks stack overflow, right? And we cannot afford to have our program crash when, I don't know, it's flying out in space doing something, whatever, right? Okay? So how can we eliminate it, right? in general, any recursive function can be rewritten as an iterative solution. For example, this Fibonacci sequence. For those who have seen it and maybe even coded it before, would you immediately jump to something like this? Or would you say, well, look at look at the sequence here. 34, what is that? Compute the last two. In other words, just keep those in memory. Keep the last two in memory. 8 and 13. Now compute the next one. 21, right? Now keep that in memory, and I can lose the oldest one. Right? I only need to keep a window here. Right? I only need to keep a window of values. So for example, let's come over here and do Fibonacci iterative. There we go. I'll go ahead and get rid of all this stuff here. Maybe keep those base cases, I don't know. Doesn't matter. Right? Otherwise, I'll go ahead and have a current int, or long, I guess, result is equal to 2, L. That's where we'll start, because if n is 1 or 2, then we would immediately return. Right? And then for int I equals 0, I is less than n, I plus plus. We're not going to start at 0, we're going to start at 3. Right? And then we're going to go up to and include n. And I need to keep track of the two previous values, right? Not the result, but current and previous. There we go. And that's going to be 1L. Actually, no, let me go ahead and start. Yeah, let me go ahead and eliminate this entirely. I like it like this better. Right? Previous and current. And then we are going to start at 1 and go up to n here. And I'm going to have a temporary variable here. Long temp is equal to current plus previous. Right? I'm computing the next one, right? So here I've got current, previous, and next. And next is going to be these two values right here. Now what can I do? I can get rid of previous by moving these two variables over into those two variables. So previous is going to end up being current, and current is going to end up being temp. And then return whatever the current is after this is done executing. Let's see how much faster this is now. Right? And just one function call, so I'll go ahead and get rid of that. Well, let's do some regression here. 15 was 610. So if it's correct, we should still get 610. Ah, darn, we're off by 1. Are we? 1 and current is equal to temp. Where am I off? 1, 1. So, oh, I know. I'm at 1, so I should start at 3. I should have started at 3. Is that correct? Let's find out. Yay, I did it. Right. So this is Fibonacci of 1, Fibonacci of 2, Fibonacci of 3 through n. All I'm doing is an iterative solution here. Now, we can bump this up to, say, 20. Right. And how would I know if I'm correct or not? 6765. We asked somebody else, right? 20. 6765. Right? I'm dead on, and it didn't take me forever to do it. What if I had done this recursively? Probably won't be noticeable. Yeah. But if I bump this up to what was our limit again? 88. And let's do it iteratively. Now this is not going to take 92,000 years. This is going to take a matter of milliseconds. Why? Because I'm only doing 88 operations. That for loop is only going to execute roughly 88 times, right? Rather than billions and billions and billions and trillions, or whatever this number is right here. Okay? So you can do that with any recursive function. You can rewrite it as an iterative solution. You can always simulate recursion. You can simulate recursion using an in-memory stack. Okay, and that's just a data structure. We'll talk about that later, because what I want to show you is you can eliminate you can eliminate redundant work by using memoization. And I just looked this up because we were doing it in CS3 too. And it's not memorization. It's not, I mean, it has the same Greek root or whatever, Latin root, whatever it is, or memo, right? Think memorandum, right? You are memorizing something, right? So it is kind of like memorization, but it's like, it's more of, it's taken from the word memorandum, okay? It's not just a bastardization of memorization. Basically, it means that instead of recomputing these same values over and over, you store them or cache them in memory, right? In a table. Right? Then, when you execute the recursion, before you execute the recursion, I should say, before you execute the recursion, you check the table. Has this value been computed before? Right? If so, you don't make the recursive call. Why would you? You've already computed this and you've stored it. Here's Fibonacci of 5. I'm not going to make a recursive call to Fibonacci anymore. I'm just going to take whatever's stored in that table and use that value. Right? If not, pay for the recursion. Okay, we don't have the value. I'm going to have to pay for the recursion, but you then store it once computed. Again, you cache it. You put it into a cache memory. Okay. We have enough time here, and we'll continue this next time as well, but we have enough time here to do a demonstration on how you would do that in say, C. Right? So once again, let me go ahead and copy and paste this entire thing, and let me create another Fibonacci version, but with memoization. All right? Now we're going to take two values in here, n, but also a table of values, right? Long table, or I'm going to call it my cache. Right? Why am I calling it my cache? Because that's where I'm saving something. What is, or cache, right? It's a storage, right? If you're caching a bunch of things, you are storing them somewhere, right? I'm going to go ahead and get rid of this and the error handling here. That's just fine, right? So what I'm going to do is I'm going to look first in the cache, right? Check the cache, right? If Fibonacci of n is stored in the cache, return it. Return cache of something. There we go. I'm just outlining this code for now. Otherwise, right, you're going to have to pay for the recursion. There we go. Now, if it's 1 or 2, we can go ahead and just return one. But otherwise, I'm going to go ahead and make a recursive call to this function, not to the other one. That other one was really inefficient on n-1 and n. But instead of immediately returning it, I'm going to store it, each one of these. Long b is equal to this. There we go. I'm going to store both of those. And then the result is going to be a plus b. And then I'm going to put the result into the cache so we can use it the next time we ask for it. ... Right? Otherwise, just return it. Return the result. Now help me to come back and fill in these blanks here. So I've got this table of values, right? How do I know that it's already been computed? Well, if it's in there, right? Fibonacci of 15 was what? 6, 7, 6, 5, right? Is equal to that. Well, that's how I know that it's computed. Like, okay, check the table for the 15th value oh, Fibonacci of, okay, it's 6765. I know that that was computed at some point. How do I know that it wasn't computed at some point? I probably need some sort of a flag value, right? I know that it's computed if I see 6765, a non-zero number. Right? If it's 0, I'll just say, okay, well, it must not have been computed. Why? Because do you see 0 anywhere inside that sequence? Nope. That's a good flag value to indicate that it has not been computed, right? In the cache, 0 indicates not yet computed, right? Otherwise, computed. Use it. ... All right? So if it's stored in the cache, meaning that it is not equal to 0, cache sub n is not equal to 0, then I will return cache sub n. Now, why am I using n? Because that's what my input is. I want to know, is the nth Fibonacci number computed? If you want to rename this to I to show the connection to an actual loop, you can do that. Right? I'm going to go ahead and keep it with n because it's more mathematical. Right? Otherwise, you pay for the recursion, but before you leave, cache sub n is equal to the result. So put the result into the cache so that you can use it later on. There we go. Now down here, I'm going to have to completely rethink how I call Fibonacci using this memoization technique. I'm going to have to pass in a table. To do that, I'm going to have to create the table. Create a table that holds n plus 1 values. Right? Why n plus 1 values? So mathematicians will generally start the indexing at 1. Right? Fibonacci of 1, Fibonacci of 2, Fibonacci of 3, Fibonacci of 4. We're not mathematicians. We are computer scientists. Right? Actually, anybody has a math double major? Okay, 1, 2? All right, good. I was a math major, so. So I have the perspective that they are wrong, right? We do not start our indexing at 1. We start our indexing at 0. Why? Because of how memory works. For that reason, we need to create it so that it's one size larger. 0 will always be ignored. 1 will be Fibonacci of 1. 2 will be Fibonacci of 2, et cetera, right? So the way that we're going to treat this is long cache is equal to long star malloc size of long times n minus 1, or plus 1, excuse me, right? Because Fibonacci, or the cache sub 0, will end up being ignored. Right? Cache sub 1 is going to be Fibonacci of 1. Cache sub 2 is going to be equal to Fibonacci of 2, etc. So now we don't have, remember I got rid of those base cases, right? Well, I didn't get rid of them, but we could now. Right, I'm going to set this up so that the table has those base cases in it. Cache of 1 is equal to 1L. Cache sub 2 is equal to 1L. Right? And the rest of them, I will let my function take care of those for me. Okay? I do need to keep track, though, for int I equals 3, I is less than n plus 1, I plus plus. Cache sub I will end up being 0L. Why do I need to do that? Because it could be garbage values. I want to make sure that they're all those flag values of 0. All right? Now let's see if this works. GCC. Uh-oh. Too few arguments, duh. So where's my memoization? There it is. I need to pass in the cache and cache. And by the way, can I make it const? Not if I want to put stuff into it, right, and change it. GCC, there we go. And there, some very, very large number, which I assume is correct. It looks kind of familiar. Okay. but in a matter of like milliseconds, microseconds, instead of whatever that was, 92,000 years. Right? So you have the best of both worlds, right? You have people saying, well, there are disadvantages, me, right? You have people saying there are advantages, that dude that really loved it, right? Well, okay, we can find a happy medium here by not eliminating the recursion, but eliminating at least the redundant work by using memoization. Yes, you can have your recursive cake, and you can eat it too by making sure that you're not doing any redundant work. Now, a lot of the risks that I just mentioned are not solved. For example, you still end up abusing the call stack to do your work. Even a moderately deep recursion will still risk stack overflow. Right? And we'll see that on Wednesday when we do this in Java, because I do want to show you a big integer in Java. Right? You will not be able to, for example, compute Fibonacci of 10,000, even though it will be computationally possible to do so, or feasible to do so. Why? Because you just can't go that deep. You can't go 1,000 or 10,000 recursive calls deep. It's just too much. Right? All right. Any questions? No? All right, then. One last thing that I'll mention, I can mention it next time too, but you're going to be basically doing the same thing that we just did, but on Hack 12, but you'll be doing it for binomial coefficients. So I just want to make sure that, that everybody understands what they are. Otherwise, make sure that you carefully read the handout. Have we seen this notation before? No? Okay. That's n choose k. On your calculators, you might have seen it as, say, alternatively here, say CNK. Have you seen that notation before? Right? Okay. That's choose. N choose k. If I have 10 things, how many ways are there of choosing 5 of them? Right? If you have 50 things, how many ways are there of choosing 3 of them? Right? That's a combinatorial binomial coefficient. Sometimes people have seen it as, say, CN underscore k. Yeah, so have you seen that one too, maybe, on your graphing calculator of some sort, right? It's not that important to understand, the combinatorics behind it or the derivation of it. Just understand that there's one way to compute it, which is n factorial. 5 factorial would be 5 times 4 times 3 times 2 times 1. Divided by n minus k factorial, In other words, these are huge numbers, right? Or can be huge numbers. One way of doing that is recursively using Pascal's identity right here. Pascal's identity says that if you wanted to compute n choose k, all you have to do is break it down into 2 problems recursively. N minus 1 choose k, and n minus 1 choose k minus 1, and just add them together. Very, very similar to what we just did up here. So instead of using that notation, you can use this notation. C sub n minus k, or comma k is going to be C sub n minus 1 k plus C sub n minus 1 k minus 1. Right. Now that should look really, really familiar because it's almost exactly the recursion on Fibonacci, except that you're taking now 2 inputs. If you take 2 inputs, what do you think your cache should look like? No longer just an array, right? Because that was n, right? Now you've got n and k. So what does your cache look like now? A 2-dimensional array, we call them tables. Right? All right, we'll pick it up there on Wednesday.